Okay, we continue to look at what is the difference between the metal phase diagram and ceramic diagram. So the axis still same. The left-hand side axis is temperature. X-axis will be the composition in WT. And then the phase is almost the same, like the example that we show you in the class. On the top is liquid, on the below is solid, in the middle is liquid plus solid solution. Okay, so this one you should able to do the timeline, you should able to do the phase analysis, LOS analysis, and so on. You should able to do. This is another one. Okay, this is the first one is aluminum oxide, chromium oxide. And again, just a reminder, if you see the word chromium, most of the time is a standard steels, related to standard steels. Stainless steel. Second one will be magnesium oxide, aluminum oxide. So you look at the bottom of the graph, it will tell you WT percentage of AlO3, aluminum oxide, mixed with MgO, magnesium oxide, temperature, and so on. On the top is mole percentage. Okay, so you already forget what is mole percentage. Go back to, I think, chapter 2 or chapter 3. Go back there. So here you should able to tell where is parenthetic, where is eutectic, and so on. Okay. So the rest you read. So this is just to highlight. There is a solubility of MgO in AlO3 in this region. Very, very small solubility at temperature of 1400 degree, about here, very, very small. So even though you pour the MgO a lot on top of the AlO3 at 1400 degrees C or less than 1400 degrees C, you will see like a Milo powder on top of your coffee or something. Okay, it won't melt inside there. Okay. So it show you the eutectic point. Okay, so there is a eutectic point here. This is another one, zirconia, calcea. So same, you should be able to identify where it's eutectic, parenthetic, eutectoid, and all these things. Okay, so get familiar with all these graphs. Okay, so if you see the slides, they'll tell you one eutectic, two eutectic, eutectoid reaction. You should be able to find where the things. So there is a table that I ask you to go and look at. Okay, you compare, you print out the table, and then you compare in the phase diagram. The table won't be given in the test, right? This is another example, silica alumina. Okay. So again, just the info on the right-hand side. Okay. So we have done with ceramic already. We have done with ceramics. Let's see, today we can complete composite. Okay, then we have more time to do revision. Okay, so composite material, it will be, you imagine as a sandwich. You have two materials squeeze each other, each squeeze one layer of each other. So the definition, this one you read lah. Composition material is a mixture or two or more constituent with a different structure or chemical composition, cannot insoluble of each other, means each other cannot be dissolved in each other. Okay. Have a clear interface separating them. So there's an interface here. So this one is not necessarily solid state. It can be liquid state. Also can become composite material. Means if you see 3 layer of things or 2 layer of things, that also called composite. Gases cannot see lah. Gases cannot see, but at least solid and liquid, you can form a material. It can form a composite material. Okay. So there are two classification. If you have one or more phrases, then they call reinforced state. So if you have another one is called matrix phrase. This one we will go deeper when we go into the tutorial question. Okay. There is no one way of classification of composite. It depends on what you want to focus on. So it depends on the type of the composite, shape of the composite, size of the reinforcement phrases. Okay, so I just summarize this chapter in one diagram for composite. The only two material inside here, which is matrix and fiber. Only two things, either matrix or fiber. There are only two things. Okay, so this is called binary system. Of course, you can have more ingredient there, but we don't go deep into more than two. Okay, for this module. Okay, fiber, you know lah, like a long fiber, long things, like a string. So string, well, the purpose is the benefit of string, is very good in tensile. You're able to pull it. What is the purpose of matrix? Matrix is to join the fiber together. It's like glue. You put in glue inside the a string. You want to glue them together. Okay. Matrix is like a glue, or you imagine as your jelly. Jelly, when you try to break, it's very easy to break. Like you take a spoon to scoop the jelly, right? So it's very easy to break away, but they're able to bond the fiber together. Okay. So when you get two value, stress value, so when you have a stress, means you either pulling it in a certain way. So you're pulling the matrix and fiber in a certain way. So let's say you get megapascal and you value 1, value 2. Let's say this one only have 20 megapascal. Most of the time, higher one will be fiber, lower one will be matrix. Okay, this is a typical analysis. But sometimes matrix will be higher than fiber, but very rare, very rare. Okay, because sometimes in the composite question, you ask you to guess, ask you to make decision, which value is for fiber, which value is for matrix. Okay, so this will be the matrix solution or summaries of what is composite. Of course, there are some formula later. I think two only. I think two formula. Okay. Okay, so advantages, you go and read lah. So this one will be the advantages of composite: lightweight, strong stiffness, specific moduli, and specific strength. Okay, and number 4, and so you can control. So what are the two major disadvantages? So this one you need to read lah. This one usually in the section A asks you what is the benefit of what is the advantages and disadvantages of composite. List out two from here, two from here. This one cannot run because I only give you 2, right? So low ductility and low impact resistance. Okay. Now, why impact resistant? Because when you punch it, you are actually breaking the matrix already. Okay. Since the slide showing you specific modulus or moduli, the equation will be E modulus Young or modulus elasti is E. If there's a specific word there, you divide the value by the density. Okay. Now, so same with strength. Ultimate tensile strength, if you have the word of specific, you divide the value with density. Yeah. So these are you only see this one in composite material, specific modulus and specific strength. Okay, so example 4, you are making a cavalier for armor and all these things, right? So unidirectional cavalier 49 fiber composite contents of 60% volume of cavalier fiber and 40% epoxy resin. So again, on what I write on the whiteboard here, composite, you have only two main ingredients, either matrix or fiber. Sometimes matrix, the name is resin, but more common one is matrix. Right? Resin is like a glue, super glue. So epoxy resin is a super glue. Density is given. So when density is given, you can find the mass or the volume. So by a density is given. So it asks you, what is the weight percentage of cavalier 49 and epoxy resin in a composite material? It asks you to find weight percentage. Okay, 100% will be the total. If you mix these two together, you get 100%. Right? And then it asks you what is the average density of the composite. Okay, so it goes like this. You assume you have something. So for chapter 10, composite material, you need to assume something like what you have in the weight percentage chapter. You assume you have 100 grams of something, then you solve the question. So here also same. Why we use 1 meter cube? Because we are given the density in meter cube. Okay. So here, why we use 1 meter cube? Because the question gives you megagram over meter cube. So in one meter cube of composite material, how many meter cube you have in cavalier? You have 1 meter cube of is 1 meter cube. You have 60% Kevlar. You have 40% epoxy. You should able to find how many meter cube of Kevlar, how many meter cube of epoxy, right? So you have 0.6 meter cube of Kevlar, 0.4 meter cube of epoxy. So when you have meter cube, you have density, you're able to find the weight lah. Okay. Now density is what? Density is kilogram over meter cube. So to find mass equal to rho multiply V. Okay, you already have V here. You have the density given in the question. You're able to find mass. Okay, what is weight percent? The object weight or mass divided by total mass multiply 100%. Okay, so here you multiply by the rho. Here you can get how many kilogram? How many kilogram? Total you put in here. Take this one put on top, you get the percentage of weight of that particular things, right? So this still go back to the previous weight percentage chapter. Okay, so the first one, I go very fast. You should able to get the answer. Total mass is 1.3 megagram. Of course, you can put in kilogram if you want. Okay. So weight percentage is 64.9%. Again, 3 decimal place or 3 significant figure. So when you get 64.9%, you should able to find another half. You take 100% minus 64.9%, or you do the calculation by taking 0.48 divided by 1.368. You get the resin weight percentage. Okay. Any question for the first part? Okay. So once you get that one, you want to find the average density of the composition of the composite. So how do you find? How you find? Okay. So the density equation, density of the composite will equal to the mass divided by volume. Mass divided by volume is a density definition. So the total mass is what? Is this one. Okay, these two components you join together in 1 meter cube, you have 1.3 megagram. Volume is 1 meter because you assumed 1 meter just now. You divide by 1, the answer will be 1.368 megagram over meter cube. Yeah, any question? Quite direct, huh? Okay, this one just for info on comparison, because we train you become engineer, you should able to give suggestion. What are the alternative material if we have a certain operation? So this one in tensile stress versus tensile strength, this is a tensile diagram or tensile curve. So here you have straight line and then there's a curve. Yeah, so these are just tell you different composite have different properties. This one also same. Only just need to highlight that the specific tensile modulus is you take tensile modulus divided by density. This is on the left. Tensile strength also same. Tensile strength divided specific tensile strength is divided by density. So these are all the material that is on the graph here with the dot. The dot. So there will be a question, especially when it comes to the last question 4. You begin a chart. You need to do material selection based on the scenario. They give you one operation condition. You look at the graph. You do some analysis, some calculation. Then you tell me, suggest 3 possible material that fit the condition. Okay. Okay, so this one already explained just now on the whiteboard. You take fiber plus metric, you get composite. Okay, the rest you read. The rest you read. So this one will be another that we call it dynamic test. Okay, dynamic test. So this will be this is called fatigue properties. Left will left right. Left right axis will be maximum stress. On the right will be the unit SI. On the right will be imperial. And the x-axis will be number of cycle of failure. It means you hit it very a lot of time. So for example, this one, all these are 10 power something. The minimum will be 100. The up to 10 mega cycle. Very fast. You hit it very fast. Okay. Or lots of time. So this one, you can see that epoxy here, it can handle in a very, very small cycle with very high stress. Okay. So these are the arrangement of your fiber or your composite. On the left, this is called layer. When you see layer, so we call it laminate or laminar material. If you go by layer, so layer means laminate, no? Laminate. So on the left is unidirection. Uni means there is the same 0 degree, 0 degree, 0 degree. Cross-pile quasi-isotopic means you have a different combination of angle. Okay, 0, 90 degree, 45, minus 45, minus 45, plus 90 and 0. Both form a laminate fiber. So this one also might be come out in the section A kind of question, ask you to illustrate unidirectional and cross-pile quasi-isotope composite with a diagram. Means you draw left diagram, right diagram. About 5 marks. Okay. Just to test you on theory and all this. Now, then we start to do some analysis already. Okay, I think we can finish chapter 10 today. Okay, so there are two scenarios of composite material. It depends on the way you load it, the way you arrange it. The first condition, we call it iso strain. Later, we'll have iso stress. Okay, before we move forward, there are two conditions of composite loading, iso strain and iso stress. Iso strain, again, the word strain is a deformation. Equal deformation. And this one will be like layer. You see the orientation is like this. Where is the loading? The loading will be in this direction. This will be load. Load can be stress. It can be force. Load can be two. Stress is in megapascal. Force is in Newton. You need to know how to convert force into stress. Okay. Stress equal to force divided by area. This one is perpendicular to the area. So this one is the normal stress. If you take the wrong one, it becomes shear stress. Okay, it depends on what you define. So this one is tensile loading. You arrange by this one. So it tell you the metric layer, fiber layer. So your fiber, metric, fiber, metric, fiber, matrix. And you have the length of your composite. This will be the area of composite. Okay. So this will be the area of your composite area. So load, if you're given area, you should be able to find the force of pulling before it fails. Okay. So this is a laminar composite. We want to find the stress on the material that cause uniform strain of all composite material, because this one, you layer by this one and you pull in this surface. So all these will have the same deformation. You will pull in this direction. Same. So assume the bonding remain intact, means you have a very strong glue, strong interaction. So this is called isostrain condition because it's bond to each other and you pull in two different directions. Then you will pull at the same elongation. Strain always linked with elongation. Okay. So we will derive the equation that link with all these parameter. we'll play with elastic modulus E. We have two materials, so we have one for fiber, one for matrix. Volume percentage, you have three parameter, which is the total volume, which is composite volume, equal to fiber plus matrix. It must be all this volume fiber plus volume matrix. Then you get the total, this one. Okay. So how do we derive? You know that the force acting on the composite was handled by fiber and matrix. So if you have a load of force on the composite, it was equally handled by fiber and matrix. And you know the stress, because the diagram gives you stress. Stress equal to force divided by area. Substitute there. Force equal to stress divided by area. Pull your A to the left. Your F become stress A. Need to pay attention to the area here. The first term here for fiber, you need to use the area of the fiber. The matrix here, you need to use the area of the matrix. Okay, so the length of the layer of matrix and fiber are equal. So the area can replace by a volume fraction V, because the length of this one, the length is the same. Okay, so you can use a volume fraction. You can change the A to V, because it's very, very hard to measure area. It's very hard to measure area. So it's more able to do volume. Why volume? Because all material have density. When you mix composite, you actually it's more easier. You measure the weight of the material. It means you pour the matrix. You weight the fiber like 100 grams of fiber, 100 grams of matrix. Then you pour these two material together and mix, rather than you go and cut the area and then join. Is very hard. Okay. So the purpose of finding volume is because it's more transparent when you communicate with the operator. You as an engineer, you need to tell the operator what to do, right? So you need to develop the manual of mixing and all these things. So you need to tell the operator, okay, mix how many grams of A, how many grams of B, mix them together, right? Okay, so you know that VF plus VM equal 1. This is a volume fraction. Let's say you have 40% of fiber, you should have 60% of matrix. Okay. So for isostrain condition, assume good bonding. This one, you will get a strain of composite equal to fiber equal to mass. Under isostrain, you need to write this equation. Means the strain equation, composite means deformation of the total composite will be the same as experienced by fiber, will be the same as the matrix. There are two equations. One is from the force equation, you derive, then you get the stress volume. And another one is a strain. So you get two equations there. Okay, you get two equations. Then you divide, then you divide the equation. When you divide stress over strain, what do you get? You still remember the Hooke's law? What is Hooke's law? What is Hooke's law? Stress equal to E strain. So if you divide stress with this one, what do you get? You get modulus Young or elasticity. Okay, you divide 1 with 2. Okay, 1 with 2. So you get stress divided by strain. This one, stress volume divided by strain. This one, stress volume divided by strain. You arrive at this equation. Stress divided by strain get modulus elasticity. So this one you get modulus elasticity. This one you get modulus elasticity. Because you're able to find the EF/EM in the material encyclopedia or material properties table. Okay, so this equation is important. E C equal to EF VF plus EM VM. This is on isostrain condition. Okay, so this equation is also known as binary system equation, equation of mixture, only apply when you have two component, which is matrix and epoxy, or matrix and fiber, epoxy and fiber. You only have two things, then only you can do this one. Okay. So in a test or in a final exam, you need to derive this equation from the front, like from the force. You need to write force equal to something, derive until here. Then you see what is missing from the question. Either I give you this one, you work back to find the force, or I give you the force, you work back to find the modulus of the composition of the composite. Okay, so it's good you practice from the force, you write from the slides just now until here. Then you read the question. What is missing? Okay, then you substitute only lah. And substitute value. Okay, so this is isostrain. So equation load So the ratio of the loads on fiber matrix region of this binary composite stress under isostrain, you can use this equation. Okay, you can use this equation. So F divided by F is the force, because it's isostrain. Isostrain is the same strain, same deformation. So force on the fiber divided by force of the matrix will equal force equal to stress area. Then you write what is the stress. Expand this one using Hooke's law. So stress equal to modulus Young and strain. Okay. So you know the answer isostrain. Isostrain means these terms and this term is the same, means strain fiber and strain matrix is the same. You can cancel. So once you cancel, you get EA fiber divided by EA matrix. This one you can, sometimes the question will give you load ratio. It will give you load ratio, means you need to write fiber F, expand this one using the mechanical properties equation. You derive until here. Okay, so you have a left-hand side value, you have area, you're able to find, or sometimes the area so and so, right? So this one will be 1, 2, 3, 4, 4 unknown, but EF, EM will be given in most of the time in the paper form. Okay, and because in isostrain we assume that the length is the same, the length that you cut out for analysis is the same, so you can expand the area into volume. Okay, so sometimes if the question do not give you area, you can solve in the volume. Yeah, so this is a very important, this one, the top one and the below one is an important equation for isostrain condition. Okay. Okay. Now I think today we look at isostrain, then we call it a day. So He asks you to calculate modulus of elasticity. Three things: the load carried by the fiber for the following composite material stressed under isostrain condition. You are given the scenario. Composite consists of two things: fiber and resin. So produced by using 60% of fiber. So 60% fiber. You know 40% is matrix already. You are given modulus elasticity EF, tensile strength of the fiber. Resin also given, EM is given. Tensile strength is given. Just remember, one is a bit higher. This one is kilopascal. This one is 9 kilopascal. This one 350 kilopascal. But again, it's good you start practicing right in the very basic form. Okay, first, modulus of elasticity for the composite. So you write this one. This is under isostrain. Isostrain, you write EC equal to EF, EVF plus EVM. Okay, this one is under isostrain. Next lecture, we'll look at isostress. Don't confuse the equation. Okay, you have the EC. Do you have EC? You don't have. But you have the volume fraction here. So 0.6 is what? 0.6 is fiber. So you have this one. VF means a volume fraction. You bracket 0.6, 0.4. EF is given. Substitute, you get EC. Okay. What about tensile? Tensile strength. Okay. So I just highlight here before I forget. Sometimes the question, we will use the word, the subject or the sample is stressed in the longitudinal direction, or it asks you to find elasticity, modulus elasticity in longitudinal direction. Then you use this formula. Sometimes it do not tell you whether it's isostrain or isostress condition. It will ask you to find modulus elasticity in longitudinal direction. Longitudinal direction. You pull in this. Okay, so means this layer, it was pulled in this direction. I just give you a head ups for isostress. Isostress orientation will be like this. It's a different sandwich orientation. Okay, so we'll look in isostress next lecture. Okay, so this one is okay. Second one, tensile strength. Use back this equation. Okay, tensile strength. So tensile strength VC equal to VF fiber VM matrix. So in this case, you know that VC is 1. VC is 1. This 0.6, 0.4. Stress is given. Substitute, you get answer. Something Pascal. Okay. Fraction of load. This one is use back the equation just now, the last equation. Then you substitute the value. So here, it asks you fraction load carried by the fiber for the following material, because you don't have the matrix force. Okay. It asks you fraction carried by the fiber. Okay. So you modify a little bit this equation into this one. So there are two things lah. Okay, either this one or this one. There is a derivation step to convert this one into this one. I just keep that lah. So this one, if you can either use this one or this one, but you already have you don't have this one. So you have the fiber and matrix E and V. So you use FC. Okay, you substitute, you get 0.97 lah. Okay, so we stop here. We continue isostress in next lecture. Okay. Sign your attendance.